Hi everyone, and welcome to the Photochemical Isomerization Lab for BYU Chemistry 353. So the reaction that we're doing today is actually a really interesting one. We're taking a trans-conjugated alkene, this trans-dibenzoylethylene, and we're going to be dissolving it and letting it sit in sunlight, and that will cause it to actually isomerize to the cis alkene. This is really a neat reaction to observe because the trans compound has a really strong yellow color and the cis compound is colorless. So we'll actually be able to observe a color change over a couple of days as we let this sit in the window. So some of you may be asking why we don't go backwards, because typically cis alkenes tend to be more strained and less stable than trans alkenes. Well, the answer has something to do with molecular orbitals. So when we set the trans molecule in the sunlight, it's able to absorb photons from the light, which promotes electrons from its highest occupied molecular orbital up to the lowest unoccupied molecular orbital. So instead of having the HOMO have 2 electrons in it, the HOMO and the LUMO each have 1 electron in it. Now this essentially breaks the double bond in the alkene and allows free rotation around that bond where the double bond used to be. Now what happens is eventually this electron is going to relax and is going to come back down to the highest occupied molecular orbital and reform the double bond. Now this can happen in one of 2 ways. Perhaps a majority of the time when this relaxes, we're going to reform the trans compound without generating the product, because everything up to this point is essentially reversible. However, if the compound happens to be in the cis orientation when the electron relaxes, the compound is going to be locked in that cis orientation. And the reason is because on the cis compound, we have the double bond, and then we have 2 carbonyl oxygens. Now these oxygens are really close together and there's a lot of steric clash there. So if we're looking down the molecule from the side, what we're actually going to see is that there's a little bit of a twist to the molecule. So the oxygens are going to look a little bit offset like this. What this causes is a break in conjugation so that this double bond isn't conjugated to the rest of the molecule. That increases the energy gap between the HOMO and the LUMO, meaning that it requires a more energetic photon to promote an electron from the HOMO to the LUMO. Now we would need a photon of UV light in order to be able to cause that promotion, and because we're doing this inside and because glass absorbs UV light, there aren't any available photons with enough energy to be able to cause the isomerization to be reversible. So anytime we form any of the cis product, it's going to be formed irreversibly, and that's why we can collect it and isolate it. So there are a couple of techniques that I want to talk about that I'm going to be referencing throughout my video today. The first is recrystallization. So recrystallization is the method we use for purifying solid compounds. And it has a couple of key steps. So we take our crude compound and we're going to dissolve it in a minimal amount of solvent at a high temperature. And what this is going to do is it's going to form a supersaturated solution so that as we cool it, some of the dissolved crystals are going to start to come back out of solution. They're going to precipitate and recrystallize. The goal is to cool this off slowly so that the crystals form gradually. The reason for that is because as the crystal matrix is reforming, as these crystals are coming back together, any impurities that may have originally been present can be excluded from the crystal matrix if the crystal grows slowly. But if everything precipitates rapidly, there's no selectivity, and so the crystals aren't going to be any more pure. the key to a good recrystallization is choosing a solvent that doesn't dissolve a lot of your product at room temperature so that you're able to recover most of your crystals. Because if your solvent can dissolve a lot of your crystals at room temperature, you're never going to get those to come back out of solution. So I'm not actually going to be doing a recrystallization today during the video, but over the course of this experiment, at the beginning, all of the product is going to be dissolved in ethanol, and by the end of the reaction, a lot of crystals will have crystallized out of this solution because our compound isn't super soluble in ethanol at room temperature. So because of that, you're going to see a lot of nice crystals form, and I'll show you those, and those are a result of essentially what amounts to a recrystallization. So the next thing I'm going to be doing today that you probably haven't seen before is taking a melting point. Now, we have another video about this called Chem 353 Melting Point Tutorial. You can find it on YouTube. There should also be links to it on Learning Suite. But just to give kind of a very basic overview, what I'm going to be doing is I'm going to have a really skinny capillary tube with a closed end. And down here in the bottom, I'm going to have some of the solid product from the reaction. And I'm going to put it into an apparatus where I can control the heat of the block that this is sitting in. And I'm just going to gradually increase the heat and watch it to see the crystals melt. And then I'm going to record the temperature that they melt at. So it's pretty straightforward. A key thing to note is that having any impurities present in crystals lowers the melting point. So, and again, I cover this a little bit more in depth in the tutorial for melting points. And finally, the last technique I'm going to be using today is thin layer chromatography. We also have a video on this, but again, just to give you a basic overview, so we're going to have a thin little TLC plate. This is going to be aluminum, an aluminum backing with a thin layer of silica gel on the front. And silica gel is really polar. Now what's going to happen is I'm going to put some of our mixture of products, our crude mixture, at the bottom of this TLC plate, and I'm going to set it in a little bit of solvent. The solvent's going to climb the TLC plate and is going to cause our products to move up the plate as well, but they're going to separate based on their polarity. Now TLC is really, the silica gel backing is really polar, so polar things are going to interact with the silica gel more strongly, and they're not going to move as far. So for this reaction, the trans compound is going to be less polar, meaning it's going to move further, and the cis compound is going to be more polar, meaning it's not going to move as far on TLC. And you'll see an example of this during the reaction today. But if you have any questions, go ahead and consult the tutorial video for thin layer chromatography. All right, so that's all of the techniques I'm going to be using. So I'm going to go ahead and get started on running the reaction. Okay. Hi everyone. I'm going to be running the photochemical isomerization reaction today. So I have here 50 milligrams of the trans dibenzoyl ethylene measured out. And I also have 4 milliliters of 95% ethanol. So the first step is just going to be getting the solid starting material here to dissolve in the ethanol. Now the difficulty is this compound's not super soluble in ethanol at room temperature, so we're going to have to heat this up. So I have a hot water bath here. I'm just going to go ahead and immerse this in hot water with vigorous stirring in an attempt to get this to all dissolve. So, well, it's kind of a pain to get it dissolved. It is also going to be a benefit to us because we can take advantage of its low solubility to purify this product via recrystallization. So that will be something I'll talk about a little bit later. So now we've got the starting material dissolved in the ethanol. You can see it has this nice yellow color in solution. Before I set this in the window to start isomerizing, I'm actually going to take a spot of this for TLC. And we're going to be using TLC, which is thin layer chromatography, to monitor the progress of this reaction. So I'm just going to go ahead and quickly take a spot of this liquid and place it on this TLC plate. And now this TLC plate is ready to store. So because this reaction takes a week, I'm going to take a TLC spot today, and then I'm going to come in 3 days and take a TLC spot, and then for the third one I'm going to take in a week from today, so that I can monitor the progress of how much of my starting material has isomerized. Alright, so it's been a week. So as you can see, the color has changed. It's not the yellow color that it used to be. Now it's this colorless solution with these white crystals in it. And notice the crystals have crashed out of solution because, like I said, both the starting material and the product are not very soluble in ethanol at room temperature. So the more rounds of heating it up and getting it dissolved and then letting it precipitate back or crystallize back out, the more pure the product is going to be. That's a technique called recrystallization, and it's a method of purifying solids. So I'm not going to recrystallize this anymore because it's already been recrystallized twice. So I'm just going to go ahead and take these crystals and collect them and weigh them, and then take my last TLC spot so that I can characterize how far the reaction has proceeded. So for collecting the crystals, I have a vacuum filtration apparatus set up here. This has a filter here. I'm just going to turn on the vacuum, which is going to remove the solvent. And then I'm just going to take these crystals and agitate them so that they're loose and not stuck to the side of my test tube. And I'm just going to take this and upend it in here so that I can collect those crystals. Now you'll notice, if you look in there, you can see crystals on the filter there, and that's a good sign. That's the product that we want. Now, because not all of the crystals came out, I'm just going to have to kind of scrape some of them out of the bottom, make sure I get all of it. And then I'm just going to let this run for a second or two to pull off all of the solvent and make sure it's dry, and then I can go ahead and weigh it. Okay, so now the product has finished drying on the vacuum filter, so I'm just going to go ahead and take this and collect it on a weigh boat, and I'm just going to get a weight of this product. Remember, we started with 50 milligrams of the starting material, so I'm just going to weigh out the product so that we know how much we got in terms of a percent yield. Looks like we got about 22 milligrams of the product, starting from 50 milligrams of the starting material. So you'll need that data to be able to calculate a percent yield. All right, so to take this last TLC spot, I'm just going to take a few of these crystals, and I'm going to go ahead and carefully transfer them into this conical vial. And then I'm going to add a few drops of methylene chloride, and then I'll just be able to transfer this onto the TLC plate as well, so that we can visualize how far the reaction has progressed. So I've got those crystals dissolved, and I can just go ahead and take my third TLC spot and place it right there. And now this should be ready for developing. So I'm going to develop this TLC plate in methylene chloride. So I have some methylene chloride here in my development chamber. And I'm just going to go ahead and take this TLC plate and go ahead and place it in the developing chamber. Alright, so I just finished developing the TLC plate. So the solvent got to this point here. So now we're going to go ahead and take a look at this under the UV light just to see what we can see. So we'll notice, so the first day the spot we took ended up right here, which that's the location of the starting material. So on the second day we had a kind of a mixture of things going on. We had that spot there and that spot there, and still some in that area as well. So this is probably still the starting material, showing us that we have the reaction wasn't totally finished on day 2, or like the third day that I came in and checked on it, but we had formed some product, and we also had some byproduct formation up here, some undesirable contaminant that was forming. Now this third spot is the spot I took of just the crystal. You'll notice we have a massive spot here, meaning it was super concentrated, but it's centered in the same place as this, so that leads me to conclude that this is also the desired product. And we'll notice there's really not anything in that area there, which is where the starting material would have shown up. So based on this TLC, we're able to conclude that the product has formed, the isomerization is finished, we've consumed all of the starting material, and our crystals are pure. Okay, so now that we've got our crystals and we took the TLC, the next thing we need to do is go ahead and take a melting point. So I'm just going to collect some of these crystals in this open-closed capillary tube, and then I'm just going to tap them down until they get to the bottom. Just pack the sample in, need a little bit more. So now I've got a nice melting point sample there in the bottom of that capillary tube. I'm going to go ahead and take this and bring it over to the melting point instrument. So the melting point of the cis isomer of this compound is 134 degrees C. So I'm going to go ahead and preheat the instrument to 125. I'm going to have a ramp rate of 2 degrees per minute, and then for my stop temp I have it just set well above the literature melting point. So once this finishes preheating, I'll go ahead and insert it into the apparatus. Alright, so the apparatus is now preheated. You can see the ready light there. So I'm going to go ahead and take my melting point sample, and I'm actually just going to go ahead and insert it here. And I'm going to start running the melting point program that I programmed in. And we'll just wait until this is actually starting to melt. Alright, so we're up to 132.5 degrees, and if we look in here, I'm starting to see signs of the product starting to melt. It's starting to collapse in on itself and sweat, and so I can see little beads of moisture in there. Getting pretty close to the literature melting point, so it should start melting pretty rapidly here. So at 134.5, and you can see it really starting to go now, and 134.8, it's all liquidized. So everything is totally melted at just over 134 degrees. So our melting range is going to be 133.5 to 134.8. Alright, so now the last characterization thing we have to do for this compound is simply to take an IR. Now, there are some inherent difficulties in taking the IR of a solid that we didn't have to deal with in the previous labs where we've been taking the IR of a liquid. So I'm going to walk you through the technique of how to do this. The technique is called a Nugel mole technique. We're actually going to use Nugel, which is a mineral oil, to suspend our product so that we can get an IR of it. So I'm going to go ahead and take a small amount of our crystal product. I'm going to go ahead and place this on my salt plates. I'm going to go ahead and head over to our instrument room. And here I'm going to go ahead and add a drop or two of this mineral oil. Now, this mineral oil is going to add some extra signal to our IR, but the mineral oil itself is composed mostly of heptane isomers, so really the only peaks it's going to give us in an IR are going to be a strong alkane peak. So it's not going to obscure any of the other functional group peaks of our product. So now that I've added the nugel, I have to mold these plates together really well to get the product into suspension. Now, you'll notice the plates, there's a kind of a cloudy film in between the plates. The ideal goal is to not have it be like glue or like really opaque. We want it to be fairly translucent, but it still needs to be cloudy because it needs to have our product suspended in it. So I had a little bit too much product on there to begin with, so I'm going to go ahead and add a little bit more of the nugel after cleaning off one side of the salt plates. Now that's a little bit better. We've got a cloudy suspension, but it's not as thick. So this should give us fairly decent IR of this compound. So now I'm going to come over here to the IR instrument. And at this point, it's just like running an IR of any other sample. We're just going to load it in. Alright, now that the IR instrument is all set up properly, now we can go ahead and take our IR spectrum of this compound. So I'm going to go ahead and insert my sample into the spectrophotometer. I'm just going to go ahead and have it collect sample. And this will just run for a couple seconds. Now, we have our spectrum here. This looks pretty good. Now you'll notice that the alkane peak, the sp3 carbon-hydrogen peak here is really strong, and these two peaks over here are also really strong. Those are corresponding to carbon-carbon bonds, so those peaks are also due to the nugel that we used to prepare our sample. But some of these other peaks here that you can see, those are going to be peaks that are actually due to our compound of interest. So I'm going to go ahead and just label these peaks really quickly so you can see them. And so you'll notice we have this one here at 1662, these peaks here at 1598 and 1590 and 1576. Those are going to be an important set of peaks. And then that's pretty much it for this compound, honestly, at those two sets of peaks there. So, okay, so we got a TLC, a melting point, and an IR for the cis compound, and they all looked good, so we're pretty confident that we were able to isolate that compound pure. So go ahead and use the data that I've provided in this video to write up your lab reports and answer the post-lab questions, and yeah, I guess that's it.